Hello everybody, welcome into another lesson. So today we are going to talk about exponential functions and their graphs. So up till now we've been used to polynomial functions where the x was the base raised to some power a, whether that was the second power, third power, what have you. With exponential functions, you have it flip-flopped, where you have some numerical base raised to the x power, where this time the variable is your power as opposed to it being your base. And this is getting into what's called a transcendental function. So exponential, logarithmic, trig functions, all those are considered transcendental functions. And then you have polynomial functions, which are your classic type of algebra functions. But with an exponential function, of course, you have some base that's some number a raised to the x power. So let's get into an example here. Let's do probably the easiest one. Let's say we have 2 to the x power. So let's say we have 2 to the x. Well, let's plot some points to graph this, and then when I explain these to you, it's going to make more sense. So let's make x 0. When x is 0, well, that's 2 to the 0, which is a y value of 1. If I make x 1, I get a y value of 2. Now, if I make x 2, I get 2 to the second, which would give me a y value of 4. And then if I make x 3, well, that would be 2 to the third, which is 8. So you get the idea. Now, what if I made x negative 1? So that would be 2 to the negative first, which would give you 1/2. That'd give you a y value of 1/2. And then if I make negative 2 for my value of x, that would give me 2 to the negative second, which would be 1/4. So, as you see, with the negative numbers, I'm getting infinitely closer and closer to a y value of 0, but I'm not actually hitting it. In fact, there is no value that I could put in for x, whether positive or negative, and get 0. Or for that matter, a negative number. So let's draw the shape of this curve here. Alright, so there's about what 2 to the x looks like when you graph it. Alright, so I can also tell you if you graph 3 to the x, you'll get roughly the same type of shape. Really, for any base, unless it's 1, you would just get a flat line through y equals 1. We don't even consider 1 to the x an exponential function. It's literally just y equals 1, but for any other base, you're going to have this type of curve. It gradually increases. It increases exponentially the higher you increase your x values. Now, we can also talk about reflections. So let's start with 2 to the negative x. What if I had 2 to the negative x? So this would indicate a reflection in the y-axis. So if I have 2 to the negative x, that's a reflection in the x-axis. So let's pick x equals 0. You still get a y value of 1. But let's pick x equals positive 1. You would get 2 to the negative first, which would give you 1/2. If I pick positive 2 for x, I would get 2 to the negative second, which is 1/4. Now let's pick x equals negative 1. Negative 1's 1, and 2 to the first is 2. And then if I pick negative 2 for x, that would give me 2 to the positive second, which would be 4. And for good measure, let's do negative 3 for x. That would give me 2 to the positive third, which would be 8. So now you're seeing here how this is reflected in the y-axis from the original 2 to the x. And you would get this again, no matter what the base is. This would be no matter what your base is. you would see this type of reflection. Everything's reflected in the y-axis. Now we can go for oh yeah, I did want to talk about whether it's 2 to the x or 2 to the negative x if it's a reflection in the y-axis. So you notice your domain is not restricted. Your domain is literally the set of all real numbers. You could pick any value of x you want, but it's your range that changes. Your range, again, being your y value, you never do quite hit a value of 0 for y. You come infinitely close, but you never hit it. So your range is always from 0 non-inclusive to infinity. Which means then you only have a horizontal asymptote at y equals 0. Because you'll come infinitely close to y equals 0, but you'll never hit it. So every exponential function has a horizontal asymptote at y equals 0. All right. Now, let's flip this around a bit. Let's say I do the negative of 2 to the x. So I'm going to take the negative of 2 to the x. If the negative sign is not in my power, if it's on the coefficient as opposed to the power, this denotes a reflection in the x-axis. So let's put in 0 for x. That would give you the negative of 2 to the 0, which would be negative 1. All right, let's put in 1 for x, so that would give you negative 2. Let's put in 2 for x, that would end up giving you negative 4. Let's put in 3 for x, that would give you negative 8. All right, now go ahead, put in negative 1 for x, that would give you negative 1/2. Put in negative 2 for x, that would give you negative 1/4. You see, and let's graph this real quick here. So you see how this is reflected in the x-axis from the original 2 to the x. Now again, you have a domain of all real numbers. So your domain is going to be the set of all real numbers. Your range, however, it goes from negative infinity to 0. It doesn't actually reach 0, but it gets infinitely close. So in this case, your range is going to be from negative infinity to 0 non-inclusive, which means you still have a horizontal asymptote at y equals 0. Which you're going to find is true for all exponential functions in general, unless you have shifts that occur and those other things, which we'll get to in a minute. So your domain is all real numbers for an exponential function, regardless of what it is. Your range is y, any value of y except 0. That is your range. Well, it depends. I mean, it's going to be, if it was just a positive 2 to the x, your range would be from 0 non-inclusive to infinity. If it's negative 2 to the x, it would be from negative infinity to 0. But either way, you'll never actually hit 0. Now let's do a double reflection. Let's say I do negative 2 to the negative x. Alright, so negative 2 to the negative x denotes a reflection in both the x and the y-axis. So let's go ahead and take care of this. I put in 0 for x, I would get negative 1. I put in 1 for x, I would end up getting negative 1/2. I put in 2 for x, I would end up getting negative 1/4. Alright, now what if I put in negative 1 for x? I would end up getting negative 2. And then if I put in -2 for x, I would get -4. I put in -3, I would get -8. So you can see now how this exponential function has been reflected in both the x and the y-axis. And again, my domain's all real numbers. My range is from -infinity to 0, and I have that horizontal asymptote at y equals 0. All right, let's also, now, what if I have, in general, if I have 2 to the x minus h, that x minus h denotes a horizontal shift either left or right. So I just take the x minus h, set it equal to 0, and the value I get for h tells me which direction I'm shifting, left or right, depending upon whether I end up getting a positive or negative value. So let's say I do 2 to the x minus 2. So that means my starting point and everything's going to be shifted to the right 2 units. So if I put in 2 for x, that would give me 2 to the 0, which would be 1. Let's say I put in 3 for x, that'd be 2 to the first, which would be 2. 4 for x, that would be 2 to the second, which would be 4. If I put in 5 for x, that would give me 2 to the third, which is all the way up to 8. Let's put in 1 for x, that would end up giving me 2 to the negative first, which is 1/2. Let's say I put in 0 for x, so 2 to the negative second gives me 1/4. And so you see everything's been shifted over to the right 2 units. But a horizontal shift does not change your range. Yes, your domain is still going to be the set of all real numbers. Your range, since you haven't done a vertical shift, which we'll get to in a minute, that's going to be, your range is still going to be from 0 non-inclusive to infinity, giving me a horizontal asymptote at y equals 0. Now, let's say on the other hand, I do 2 to the x, that whole thing minus 2. Now I have 2 to the x minus 2. So that minus 2 beside your exponential term denotes a vertical shift up or down that many units. So general form would end up being 2 to the x plus k, of course. That plus k denotes a vertical change either up or down. Since it's minus, we'll be going down 2 units. Alright, so if I put in 0 for x, well, 2 to the 0 is 1, minus 2 is actually -1. Let's say I put in 1 for x, 2 to the 1 is 2, minus 2 is 0. And then we have 2 to the second, which would be 4, minus 2 is actually 2. If I put in 3, so 2 to the 3 is 8, minus 2 is 6. Now let's put in -1 for 2. That would end up giving me 1/2 minus 2. That'd be -1.5. Let's put in -2 for x. That would give me 1/4 minus 2. That would give me -1 3/4. So you should notice a pattern here. So what do we notice? We notice now that our domain has stayed the same. So again, for all exponential functions, your domain will always be all real numbers. But what about your range? So that vertical shift impacts your range. That does impact your range because my vertical asymptote is now down to y equals, my horizontal asymptote rather, is now down to y equals -2. because that vertical shift will shift everything. So my horizontal asymptote goes from y equals 0 to y equals -2, which means my range would go from -2 non-inclusive to infinity. Because I'll get infinitely close to y equals -2, but I'll never actually reach it. Alright, let's do one more like this here. Let's say, let's really do this. So we have -2 to the 5 minus x plus 3. We've really pulled the rug out from under you. So what's going on here with this exponential function? Look at your negative sign on the 2. That definitely denotes a reflection in the x-axis. Now, you have to the 5 minus x. That negative x also denotes a reflection in the y-axis. This is how it varies from the original 2 to the x. So we have a reflection in the x-axis. We also have a reflection in the y-axis. Now, that 5 minus x you could think of as negative x plus 5. So, or 5 minus x, rather, you're shifting everything to the right 5 units. So you have a right shift 5 units. So there's your horizontal shift. And then that plus 3 beside it means a vertical shift up 3 units. So you have an upshift of 3 units. So from the original f of x equals 2 to the x to this function, f of x equals -2 to the 5 minus x plus 3, you have a reflection in the x-axis, a reflection in the y-axis, a right shift of 5 units, and an upshift of 3 units. So let's start when x equals 5. Well, 5 minus 5 is 0. Negative of 2 to the 0 is -1, plus 3 is going to be 2. Alright. Now, let's put in 6 for 1. We put in 6 for x. That would give you the negative of 2 to the negative first, so that would end up giving you -1/2 plus 3. That would end up being 2.5. Let's put in 7 for x. Well, that's going to end up then giving you negative of 2 to the negative second, so that would end up being -1/4 plus 3. That'd be 2 3/4. So it looks like you're getting infinitely closer and closer to y equals 3, but you're not actually able to reach it. So you can actually say that your horizontal asymptote is at y equals 3. And that's what that plus 3 is. It shifts everything upwards 3 units. Horizontal asymptote located at y equals 3. Okay, let's go back to x equals 4. So 5 minus 4 is 1. Negative of 2 to the first is -2 plus 3 is 1. Alright, let's put in 3. So if x is 3, that's -2 squared, which is going to be -4 plus 3 is -1. And for one more, let's put in 2. So negative of 2 to the 5 minus 2, that's negative of 2 to the third, so -8 plus 3 is all the way down to -5. So there's about what your graph is going to look like. Whoops, it can't go above that 3. Good thing I caught that. You'll get infinitely close, but it won't actually reach y equals 3. So here is the graph of 2 to the x transformed with all these transformations to give you the graph of f of x equals -2 to the 5 minus x plus 3. Now I'm going to do 1 of 3 to the x. just to show you that all exponential functions work the same way and are basically the same. So f of x equals 3 to the x. Well, let's make x 0. 3 to the 0 is still 1. Now what about when x is 1, you get 3 to the first, which is 3. If I make x 2, you're all the way up to 9. If I make x negative 1, you got 1/3. So there is your approximate graph of 3 to the x. And as you see, it looks very similar to 2 to the x. So you would get a very similar shape no matter what your base is. Now let's talk about something else here. What if I did 1/2 to the x? What if I did 1/2 to the x? Well, let's graph this real quick. So 1/2 to the 0 power is still 1. Now let's say I make x 1, you would get 1/2. What if I made x 2, you would get 1/4. Alright, let's make x negative 1. That would give you 1/2 to the negative 1, which would actually give you 2 to the positive first, so that's 2. I make x negative 2, that would give you 1/2 to the negative second, which would be 2 to the second, so that's 4. And a very curious thing's going to happen. So it looks a lot like 2 to the negative x, doesn't it? That's because it is. Think of it this way. 1/2 is what? Isn't that the same as 2 to the negative first to the x power? Just multiply your powers. What do you know? You have 2 to the negative x. So 1/2 to the x is the same as 2 to the negative x. So if you get a positive fraction that's less than 1 but greater than 0, it'll behave as the whole number raised to the negative power. It behaves the exact same way. Let's do one more fractional, then I want to talk about the number e. So f of x equals 3/2 to the x. So we have a fraction greater than 1. Let's see what happens. So if I raise this to the 0 power, I'll get 3/2 of the 0, which is still 1. What if I raise it to the first power? That'd be 1/2. I raise it to the second power, I'll get 9/4, which is 2 1/4. I raise it to the third power, I'll get 27/8, which is going to be 3 3/8. And then if I raise this to the negative first, I would end up getting 2/3. I raise it to the negative second, I would get 4/9. And as you see, I'm getting infinitely closer and closer to y equals 0 without actually reaching it. So there is going to be my graph of f of x equals 3/2 to the x. So as long as your fraction is greater than 1, it'll behave as a normal base. If I have a fraction greater than 0 but less than 1, then it's going to behave as the reciprocal of that number raised to a negative power. So those are things to keep in mind. Now, you may have seen this in Algebra 2. We have the number e, which is approximately equal to, I know it's 2.71 something. Let me get the exact 2.71 828 ... So you have what's called the natural base, e. It's approximately equal to 2.71828 ... Alright? It just keeps going and going, much like pi does. We know pi is 3.14, and it just keeps going and going. Well, e's pretty much the same way, but e's called the natural base. The reason being is because e is used to illustrate continuity, such as in nature or in financial, like with continuous interest that compounds, or radioactivity, or such things like that. That's where the number e comes into handy. So let's just graph f of x equals e to the x real quick. So f of x equals e to the x. Well, make x 0, that's still going to be 1. E to the 0 give you 1. Make x to the first, you would get about 2.72, which would be right about there. Then e to the second, you would be somewhere in here. So your graph is going to look a lot like the other exponential functions we've done. And it's going to behave the exact same way, only it's base e. So there's your f of x equals e to the x. So really, exponential functions are pretty simple. Now the next lesson we're going to get into logarithmic functions, which are the inverse functions of exponential functions. So we'll talk about logarithms at that time, what they are, how they work, and the graphs of logarithmic functions. So I hope everyone has a great day. Take care.